Okay, so in this video, we will look at how matrix multiplication is related to linear systems. And you'll understand why we defined matrix multiplication the way we did, and you will see very shortly because it fits perfectly with linear systems. So let's start very simply with a linear system in two variables, two equations. Let's say we have 2x plus 5y equals 9, and 7x plus 3y equals 6. The question I'm going to ask now is, can we rewrite this linear system in the following form as a matrix A times another matrix X equals a third matrix B? And this would be what we consider a matrix equality. A times X equals B. Well, remember that when you multiply two matrices, you do it one row times one column for each entry, and you multiply a row times a column by multiplying corresponding entries and then adding them up. So you would have one term times another term plus another term with another term and so forth. And if you look here at the left hand side, it looks something like this. We have 2 times x plus 5 times y equals the entry 9, and then 7 times x plus 3 times y equals the entry 6. So this is the result of a row times a column. Well, the first row 2, 5, the second row 7, 3, times, well, we need a column, and the entries of course would have to be x and y. Okay, so let's see if that's our A and our uppercase X. Here, this matrix is a 2 by 2 matrix. This matrix is a 2 by 1 matrix. So multiplication is defined as 2 equals 2. And the result will be a matrix that is also a 2 by 1 matrix. So a single column with two entries. And now, let's see how we have to choose our matrix B so as to have an equivalency with the linear systems. So let's multiply this out. We have 2x plus 5y, but that must equal 9. Second entry, we have 7x plus 3y, but that must equal 6. And there you go. We now have rewritten the linear system into an equation with three matrices. A times x equals b. Of course, here we use uppercase X to differentiate from the single real variable x to the column matrix uppercase X equals a column of constants, B. And you may wonder, well, is this a fluke? Well, the answer is no, and you can see quite easily that the matrix A is the matrix of coefficients, 2, 5, 7, 3. The matrix B is the column matrix of the constant terms, 9, 6. And the variable vector, or the variable column matrix X, contains the variables, x, y. Let's do two other short examples. Suppose we had now three variables, two equations. So we'll go with 2x plus 5y minus z equals 10, negative 3x, negative 2y plus 7z equals, say, 6. We want to rewrite the linear system in an equality of this type. Well, let's use our shortcut, and then we'll multiply out the left-hand side in our head to see that the equality of matrices is equivalent to the linear system. So we're saying there are three parts. The matrix A, which we claimed was the matrix of coefficients. So the first row of A should be 2, 5, negative 1. The second row should be negative 3, negative 2, 7. Times the column matrix of variables, x, y, z, equal the single column matrix 10, 6. So that's our claim. So this is the matrix A. This is the vector of variables x, and this is the vector or column matrix of constants b. Well, first, let's see that the sizes do fit. This matrix is a 2 by 3 matrix. This matrix is a 3 by 1 matrix. So 3 equals 3. So we can multiply, and the result would be a 2 by 1 matrix. So, when we have here a 2 by 1 matrix, so everything works out. Let's multiply out. First entry, row 1 times the column, so 2x plus 5y plus negative z, check. And this has to equal the first entry, 10. So far so good. Second entry is 6. Let's multiply out. Second row will give us the second entry, negative 3x plus negative 2y plus 7z, check, and this must equal the second entry, which is 6. So it is working out. So here's the matrix A. Here's the column matrix of variables, uppercase x, and the column of constants, uppercase b. So it does work out. So now let's do one last example very quickly. And then we will not check, we'll just do it. Suppose we have 3 equations, 3 variables. Okay, so we have our linear system now, 3 equations and 3 variables. Let us rewrite this in the form of a matrix equation. So A matrix of coefficients, therefore 2, 1, negative 1, the first row. Second row, 6, negative 2, 3. And the third row, negative 1, negative 6, positive 8. Times the column of variables. Here we have 3 variables. So we have a column with 3 entries, lowercase x, y, and z. And we call this, as always, uppercase x, equals the column of constants, again a single column with 3 entries, 1, 4, negative 9. And you can check on your own that if you do multiply the first row with the column, you get the first equation. Second row with the column, you get the second equation. And the third row with the column, you get the third equation, which are equal to, respectively, 1, 4, negative 9. And there you go. Now, the purpose of this video was just to show you that the reason, again, in conclusion, that we multiply matrices the way we do is because it fits perfectly with our notion of linear systems. Later on, this will be even more interesting when we consider the inverse of a square matrix, and this will allow us to find a new way of solving these linear systems using what's called the inverse of a matrix. But this will be a topic for a later video.